Hello friends, today we are going to see an continuous topic of the data ecosystem system with the signal conditioning, that is digitization. Digitization, it includes aliasing, quantization and the sampling phenomenon. So the digitization phenomenon included three wide topics. Start with the sampling, then aliasing and then quantization. So we already know what is sampling, what is the process of sampling, what are the types of sampling. Now here in this topic we will see details and the some introduction part of the sampling, also the detailing form of the sampling, how it is correlated with the aliasing, how it is again correlated with the quantization process. First of all, we have to know the digitization need. Means what? Why digitization is required? Why does an every engineer need to know about a digitization? Digitization simply sampling, aliasing bits or bytes, and that is the quantization. First, as an educated person should know how all the digital services or the devices we used every day. So simple thing, the simple whatever the instruments or the device or gadgets we are using, the computer, cell phone, TV, camera, CD, DVD, all these are in the digital form of the audio and video signals. So an educated person, we have to know how it is converted all our analog signals into digital form. It is a digitization. Now as an our subject point of view, every engineers, whether it is mechanical engineers or civil or an electrical engineers, it should know a computer control or the power domain, where a power from the power domain, different signals which are taken at the sensor through the process or through the actuator, whatever the signal it has taken with respect to the communicate with the control room and with the information domain, it is have to send that particular signals into computer, digital to analog or analog to digital converted through digitization. Means what? For the digitization process, whatever the signals coming through the plant, whether that particular signals through the actuators, that particular signals coming from the sensors, or again to communicate with that signals of the actuators or the sensors, and for the communications through the computers we require analog to digital and digital to analog form. So that convergence typically are digitizations. Now digitization, as I am saying earlier, having three forms, that is the sampling, aliasing and quantization. So see, understand the things, that is then start with power domain. In power domain, whatever the signal is coming through the actuators, through the plant, and whatever the signal coming from the plant is can be sensor, it can be pressure sensor, it can be volume sensor, it can be displacement sensor, it can be temperature, or it can be a light sensor. Then whatever the signal coming from the actuator, that can be a DC motor, synchronous motor or three-phase induction motor, whatever the signal is coming, that is coming directly to the aliasing filter, and that aliasing filter filtering desired signals sampled, or you can say converted, or you can say it can be reformed with our resulting signals and that converted into analog to digital form. So after the analog to digital signal, it is going to a digital computers, and while it is going to analog to digital converter and to digital computer, two processes happening, that is the sample and quantization. So that is the topic, today's topic. But while coming the signal into analog to digital converter, another signal is coming digital to analog converter also, and that can be a sampling system. So in the sampling system, we will communicate with the digital computer. It can be receive the signal or it can be send the signals, while the same way from to digital analog to digital converter, that converter to the digital computer, the sample and quantized process is happened for the measurement. In the same way, digital computer to the again digital to analog converter, again the process is happened, that is the sampling and the quantization. Now understand the thing is that the signal which are coming from the plant, and plant is very far away from our control room, and in control room the computer peripherals is there which control, or you can say seen that particular value in real time process. So digitization is analog to digital or to digital analog conversion process is there. Now here I am again saying it is a real time phenomenon. So while the real time phenomenon, not a one signal is coming, it can be various signals. So the various signals when it is coming through the plant or while coming signal from plant to the control room, it can be a complex. So the complex decision making is happened. So here computer, obviously in computerization, software and electronics part is there. Now the instruments, it is from the sensor sides, whatever the energy conversion or the signal processing is happened from the sensor sides, the tell us what is happening right now in the plant. And the physical systems is there where the different signal is coming for the measurement of the electrical signals, mechanical signals. It can be a fluid, it can be thermal, it can be biomedical or the chemical signals. So through the plant this various signal is coming, and it is going through the sensor from the instrumentations where it is taken the reading, and it is again going to the computations. Now from the computations, it given signal to the actuator, and actuator makes the thing is happen with power consumption, power modulations and the energy conversion. Means what? Whatever the motor, whatever the conveyor belt, whatever the process or the production team or the department is happened, it is directly control with the computations, and obviously computations require a software and electronics part. Now whatever the signal is sync with the actuators, whatever the signal is sync of the digitization while computer with another instruments, there are various signal is there. So it can be continuous, it can be discrete. So here is our table where whatever the signal is coming with respect to time, and on other side it is with respect to amplitude. So again I am saying here is our amplitude and here is our time. But the amplitude signal can be continuous and the amplitude signal can be discrete. So, the discrete amplitude signal is called quantization, and in time the time can be continuous and the time can be discrete. So again another phenomenon, that means when the time it is in discrete, that is called sampling, that's the sampleization. Now when our amplitude is in continuous and where our time is also continuous, that particular signal is called CC, that is continuous in amplitude and continuous in time. Again, when our time is in continue and our amplitude is in discrete, that particular signal is called DC, where again when our signal amplitude signal is in continue and our time signal is in discrete, that particular signal is called CD. And when the signal both the signal is in discrete, that is the amplitude and time both the signal as in discrete, that particular signal is called DD. Now we will see in details. See, analog signal, the graph is coming in such a way where on y-axis it's our amplitude, on x-axis is our time. See here our CD signals with the amplitude with respect to time is in sampling that signal. We have taken sampled signal. Okay. Now in quantized we are taken with respect to amplitude and with respect to time whatever the signal is in discrete signal, and that discrete signal is quantized signal, that is the quantization process. While in DD, quantization and sample both are mixed together, means both the process are in simultaneous way, and that particular signal a simple our digital signals, it is here, and here is our amplitude with respect to time. Now you understand how is the quantization and the sample process is there. Now we will move our next slide, that is CD signal, where the continuous in amplitude and the discrete in time. Here is the analog signals, here is our analog signals, and we are taken the samples, we are taken the samples, we are taken the samples. This is the CD signals. Now here is DC signal. Now the thing is that in earlier slide we are taken with respect to amplitude on y-axis, but in here this slide we are taken and instead of amplitude we are taken frequency, but frequency and time are both are inversely proportional to each other, and this phenomenon is considered to taken only a digital signal form, only in digital signals where sampling and quantization process are happen simultaneously. Now here is DC signal, here is the analog signal is happening, analog signals, and we are taken quantized signals. Here is the quantized signal is happened. The sample and the quantized signals with zero order hold. Now again the concept is happened, what is zero order hold? So zero order hold, sampled and quantized values are held in constant. Here is the constant between the sampling instant, which makes the signal in discrete in amplitude but in continuous time. So time is continuous, here is our time is continuous, but the amplitude here considering the frequency is in discrete form. Okay. Now how do an engineer takes an information such as sound, picture and text. Now turn them into a number. How this happened that an engineer taken the information such as sound or can be a picture or can be a text. When it is converted into a number that can be processed by our ever increasing the computing capabilities. Now, when a digitization is in process of the representing various types of information in form that can be stored and processed by a digital device. It is the combined operation of sampling and quantization, and it is also called as analog to digital conversion. Now, a sample is a numerical value representing the height of a waveform at a particular time or the brightness of an image at a particular point. So, numerical value is the main thing here, where the height of waveform with respect to time and the brightness of an image at particular point is also considered. Now, a digital signal is a set of a sample value represented in a binary form. That a binary form is a numerical value as a bits, and that bits is a nothing but our bit width. It can be turned back into original form. So whatever the value we are converted into digital form is nothing but our a binary value. We can again regain that our original value. So from whatever the information we are taken that converted into a number is a new thing. So if we see a here continuous variation in color, light and sound digital devices while recording. So the thing is that variation in colors, variation in light and variation in sound. To capture all that signals while the recording, and at the same time the process is happened only in sequence and not in original sound, picture or the movies. Now, it is possible that information can be turned into a list of number without losing any quality. How this happen? The engineer need to deal with both the technologies and limits of the human perception. Sampling is the process of recording the values. That values is nothing but our the sampling signals of and distinct point with respect to time or can be space. Now, waveform are sampled in a time, images are sampled with respect to space, and time varying scene, that is nothing but our video signals, are sampled both in time and also both in space. So the thing is happened in three ways. Again I am repeating that the waveform are sample in a time. Waveform is another thing. Now images are sample with respect to space, and the video are samples with respect to time and space. Now here we should one take measurement to ensure that the number allow us a faithful recreate to the original informations. That means whatever the signal we are capturing with the various parameters, and that can be again recreation the original informations. So the sampling of a waveform refers to the process of recording value at a distinct time points to the analog signals. Usually, a sample of a signal are observed at uniformly space time instant. For example, every zero point 0.1 second as shown below. Here is shown here. The height of the dots above or the below the time exit in horizontal axis represent at the samples. Means what? Here is our analog signals. Here is the signal coming and low and become low, but we are taken with respect to we are taken the sampling on one another way of that particular analog signal with respect to time, and this is only for zero point 0.1 seconds. So see here 0, 0.5 and 1 second. So 0.1 second, whatever the signal we are taken here, here shown here. Now an analog signal that very quickly sample more frequently than an analog signal very slowly. Means what? Whatever the analog signal is very quick changes is happen, that can be sampled easily, and whatever the analog signal we are taken slowly, that can be taken, but whatever the sample we are taken, it can be in difficult way. So the sampling period, that is TS, is Yes, is the spacing between two adjacent sample. So it is second per sample. Again I am repeating, that it is a spacing between two adjacent sample. Two adjacent sample. That is the second per sample. Now the sampling rate or the frequency f of s is the number of sample per seconds. So here is seconds per sample and here is sample per second. So you should not be confused, because here we are taken the sample per second, but here we taken the seconds per sample. See here f of s is equal to 1 upon t. Means what? The simple thing is, whatever the frequencies f of s taken, which is sample per seconds, it is exactly inverse of ts, which is second per sample. See here, our it is our analog signal and we are taking the sample with definite interval of time, and here is our actual signal start, but it can be minus signals or it can be plus signals, and the minus signals with respect to time is t of s. Okay, so the sample value of the analog signal. Now whatever signal we are taken here is has to be taken with some simple phenomenon, that is a Nyquist sampling theorem, and as the Nyquist sampling theorem is with respect to frequency and with respect to time. Now the sampling theorem phenomenon will start. Now as I am saying, the Nyquist sampling theorem is with respect to frequencies and with respect to time, and both frequency signals and the time signals are inversely proportional to each other, then a sample signal can be converted back to its original analog signal without an error is happened if the sampling rate is more than twice as large of highest frequency of the signal. So the important thing in this Nyquist sampling theorem is that the twice as large as the highest frequency signal. Nyquist frequency, that is f of s, is t is equal to half of f of s, and it is a discrete time system property. Restated again, this particular sampling theorem, Nyquist sampling theorem, in the mathematical form is that if T of s is the spacing between the samples of f of s, and f of s is nothing but the inverse of spacing T of s, then theoretically we can convert the sample of an analog signal back into original signals if and only if f of s is greater than second large as the frequency of highest signal, where f of highest is the highest frequency signal containing analog signals. So whatever converted digital signals into an analog signals, where our Nyquist sample theorem we considering, and that particular signal f of s, that is the original signals, is nothing but highest of second of highest multiple of 2 of f of highest, and f of highest is nothing but a frequency containing analog signal. Now the value of 2 of f of highest is nothing but our Nyquist rate. So the Nyquist sampling theorem is depending upon f highest, so the highest frequency. So 2 times of highest frequency, that is the f of highest, is the highest frequency containing analog signals, that that defining a Nyquist rate is the lower bound of the sampling frequency that satisfy Nyquist sampling criteria. Nyquist rate is a lower bound of the sampling frequency that satisfy the Nyquist sampling criteria. It is a continuous time signal property. Now, as shown here, here is the table which are given. We will explain you one by one. A minimum sampling rate for various signals. So various analog signals having a various sampling rate. Here is the signal bandwidth refer to the difference between the highest frequency of the signal and the lowest frequency signal. So the difference is required in the two signals, that is the highest frequency and the lowest frequency. Now in general, whatever the Nyquist criteria rate is considering, Nyquist criteria that can be taken two times. This is the 2 of f of f highest frequency is the bandwidth of the analog signal. So whatever the analog signal bandwidth is there, it is 2 into f highest, right? And if the lowest frequency is 0, so lowest frequency is 0, then the signal bandwidth is equal to the highest frequency, that is here highest frequency f. Now here are some different type of signals for which the bandwidth is measured, and bandwidth is measured with the difference between highest frequency and the lowest frequency. Now the minimal sampling rate is already given. We know how the sampling rate is calculated and how a rate is actually used. Actual use, standard rate, and the different signal with its defined bandwidth. Start with telephone quality speech. Here the bandwidth is 3.5 kilohertz, where the sampling rate is 700 sample per second, and the rate which actually use of the analog signal is 8000 sample per second. So minimum sample from 7000 to the 8000, and the difference with respect to the highest and lowest frequency here is getting 3.5 kilohertz bandwidth. So the difference is less, so the bandwidth is also less. Now music, in the music signal 20 kilohertz bandwidth is there, where our sampling rate is 40,000 sample per second. See the thing is that, friends, 40,000 samples per second is the very much, but the actual rate is 44 to 100 samples. So the whatever the minimum and whatever the actual is not having minimum, whatever the difference is very much less, but the bandwidth for the music is 20 kilohertz, that is much higher. Now in FM radio the bandwidth required much more higher. So the samples is 44 lakh samples per seconds, and the actual rate of that particular frequency signal is 5 lakh samples per seconds. So the frequency of the bandwidth of that particular signal is 200 kilohertz, that much higher. Again, a standard definition television, television, whatever the signal is taken is with respect to image, with respect to text, with respect to audio and the video signals. Okay, so overall it can be considered as a standard definition television signals. So it is 6 megahertz bandwidth. So the Nyquist rate is from the sampling rate is 12 lakh samples per seconds, and the rate which is actually used is 14 lakh 40,000 sample per seconds. So here is the various signal with respect to their bandwidth and how minimum samples with the actual rate. Now here you understand all the things of the quantization process and the sampling form. Now in the digitization form there are another signals we have to consider, another process, that is aliasing form, aliasing process. So we have to know the term aliasing. Aliasing refers to a one signal pretend to be another signals, one signals pretend to be another signals when the samples, both the samples of that signals is the same. Now it is an undesired effect due to undersampling, where one signals can be present as an another signals. Means what? One signal is there having particular samples, another signals having that same type of the sampling happen. So in that particular situation how the thing can be done? So aliasing effect, aliasing process is there. See here, the sampling of 720 Hz sinusoidal at the rate of 660 Hz. Note that the samples appear to be coming from sinusoid at much lower frequency than does not exist, and this is called aliasing. Means what? Whatever the signals are coming below 660 Hz, that can be, which cannot be exist in actual sampling, only and only the signal highest than the 660, for example 720 Hz, that are only and only sampling, and this is nothing but aliasing. Now there are some limitations of the aliasing effect. So what is that effect of aliasing? Aliasing is a serious effect that is inevitable and irreversible. Inevitable and irreversible is the property of the samples which are taken, and the must be avoided if we are properly digitize the information. So if we have properly digitization form, this property of the signals sound surround serious effect does not happen. But if aliasing causes frequency to change, whether the signal are sound, image or can be video, then we considering a typical signals can be image or the time vary, since that the composed of many frequency, the effect are very complex, so we have to take measures to prevent aliasing. So for the effect of aliasing, what are the limitation we have to take on? That is, effect are very complex. When the effect is very complex and it is composed with many frequencies, that frequencies can be sound, can be images or can be video. So what the complex process this have happened to prevent of the aliasing. In most of the case, we can measure the bandwidth of S of t. So here is the another thing is what is S of t, where we can choose a sampling rate. So S of t is the measured bandwidth of a particular signals. We can choose a sampling rate. We can avoid aliasing by simply sampling faster than the Nyquist rate. So for every signals and every bandwidth of the sampling, we are choosing a Nyquist rate. But thus if we choose our sampling rate is much faster than the Nyquist rate, then aliasing, the effect of aliasing can be prevented. However, if S of t is not band limited, that is has an infinitely broad range of a frequency, or if we are not able to change the sampler rate, then what will be happen? Means what? The bandwidth or the sampling rate, if we can't change, then what will be the happen? It can be, we must first pass an analog signal, that is the S of t, through a device which is an analog low pass filter. So devices here we consider filter, and that particular filter is a low pass filter. So the device we are considering a low pass filter, it is an analog low pass filter which attenuate all frequency in the signal above the selected frequency and pass all the filters. Attenuated means what? It cut all the above signal frequency and passing only a selected frequency. This finite filter will reduce the effect of frequency components above half of the sampling frequency. So whatever a sampling frequency we are decided that half of the sampling frequency has to be reduced and effect of the frequency components is happened. Now such filter is called an anti-aliasing filter. So to avoid aliasing effect, an anti-aliasing filter is used, and that filter is nothing but analog low pass filter. So this filtering operation will cause the signal to be different because it will attenuate the high frequency, and that high frequency is S of t. However, we will not be able to use these high frequencies anyway because they are above the Nyquist limit. So if the signal whatever the frequency highest frequency is above the Nyquist limit, we will not able to capture that highest frequency signals. Now attenuation them prevent them from corrupting the lower frequencies that we can use, and the filter does not add time delay and thus limit system performance. So system performance having certain limitation, the filter does add time delay and limit has to be performed. See here, in there are slide is there in the next slide where S of t, that is our original analog signal, which is not band limited, and the analog anti-aliasing filter which attenuate that particular signals and giving pass only a highest frequency, that is S of t, creating a new band limited analog signal, another created, that is SBL. It is a band limited signals SBL, and it is with respect to time, that is when it varies with respect to times, and this signal is the sampled faster than Nyquist rate. This is the main thing that producing a set of samples, that is the BL. Now whatever the signal coming to the filter is S of t, but the output of that particular filter is SBL, that is the band limiting signal, but that band limiting signal is much again the sampling, and that should be sampled faster than the Nyquist rate, that is the SBL. See here with the figure that here is our S of t. Here now the low pass filter. Now here is S of BL. It is with respect to time, and while sampling it should be higher than the Nyquist rate, and we get is S of, see here we are getting S of BL, but it is in with respect to Nyquist rate. Here is S of BL with respect to time, but here is S of BL with respect to Nyquist rate. So this is the example of telephonic system. So in telephonic system, our voice is maximum with the frequency 3600 Hertz. So at our microphone, at the side of microphone, our voice is filtered by analog filter. Subsequently reduces the frequency above 3600 Hertz, and then microphone signal is sample 8 kilohertz signals. Means what? The surrounding side's sound can be more 3600 Hertz, but a low pass filtered reduce that highest frequency of 3600 Hertz and only passing that band limited frequency. And here in the telephonic microphone signals, sensors having signal 3600 Hertz. Again that signals sample up to 8 kilohertz, that the sample signal is SBL. So here is, if we hear in the background of the telephone, music will appear like a distorted. So our ears can detect about 15 kilohertz frequency, and the music generally has a frequency context exceeding 3600 hertz. So little frequency content will pass through the telephone systems. So here we consider simple, our voice signal is 3600 hertz. So while passing a low pass filter to reducing the frequency is we are getting up to 3600 hertz only and only, but here is mixing of another signal also, but we are getting at the output 3600 hertz only. Okay, but while sampling with the Nyquist criteria, we are getting with the sample signal is up to 8 kilohertz, and our ears end detected up to a 15 kilohertz frequencies and music, which having generally 3000 exceed the signals of 3600 hertz, and this is the little bit of frequency contents will pass through the telephonic system, and that is nothing but a small music or small voice we can hear. So here we end our topic, that is signaling and the aliasing. So we are understanding what is the signaling part, what is the sampling part, types of sampling, then aliasing, how aliasing effect is there, how it can be uh, come over with the Nyquist rate, and now we'll start with another part or the another a new topic, that is the quantization. This is an another important part of digitization. Now continuations of digitization part, the next part is quantization. Quantization is nothing but bit to store samples. In sampling, we assume implicitly that computer stores the numerical values of a sample of a signal exactly without any loss of accuracy or the precision. But is it really happen? Means what? Without any loss of accuracy or the precision is such type is happen. Computer stores with fewer decimal places than actual real number typically would have. This is really no different than when you take measurement is an experiment and choose to write down value using only a few decimal place. Means what? There is no difference when you take a measurement value of an experiment and choose to write down only in few decimal place. In real world, digital memory device use only a fixed number of bits. So only a fixed number of bits is there for the storage of each number, which implies limited or the finite accuracy. The accuracy achieved in storing a sequence, that sequence is S of n of number of, depends on how many bits are used to store such a sample. So storing such a samples which required a sequence of S of n. See here a sampled analog signals where a fixed number of bits is there. There is a fixed number of bits. See here 1, 2 here for the highest side and the lowest side sample is taken. So fixed number of bits is there. Here is for the also for the highest side and the lowest side, Again the sample is taken. Again for the highest side and the lowest side the sample is taken. In also between highest to low and between highest to low, again the specific interval of time the same sequence is there while taking the sampling. So as shown in this particular sample of an analog signal, binary numbers with fixed numbers of zeros and ones, we can store only a finite number of the signals. That means what? With the specific interval of time, whatever the signal we are taken from highest to lowest or the lowest to highest is a fixed numbers of zeros and fixed number of 1. We should use the smallest number of bits that will provide the accuracy we need for the given engineering application. So in engineering application we have to consider a smallest number sample that which are converted from zeros to 1 or ones to 0. So whatever the sample is taken from highest value or the lowest value, but that particular value or conversion numbers is the smallest number. I will explain you that in next slide also. See here, this is our particular analog signals, and that particular analog signals we are taken a sample with a definite interval of time. Here we are storing each sample with only 2 bits. That is the 4 possible stores, that is 0, 1, 2, 3. Okay, see here our true value, whatever quantized value we are taken, see here 0, 1, 2, 3. So whatever the quantized value we are taken is between 0 to 3. Understand? So if we are taken true value, we are taken the simple, suppose we are taken this particular sample, this we have to take a smallest value with respect to this. So smallest value is between 3. So with respect to 3 we are taken this particular value. Again we are, suppose we are considering this particular signals, that we have to consider with the smallest value. If we consider these particular samples, that we have to consider with smallest samples. Okay, so see here, in this way we can measure the accuracy and exact position, exact signaling form. We can consider any signal. Suppose here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, almost whatever the signal is there. If we consider this signal, it can be a 3.8996, no, this can be 2.4. So these signals can be 2.4183 signals. So the quantized value with respect to is 2. So we can consider as the smallest distance signals. It can be conversion is 1 0. So why it is happened? Because whatever the value we are taken quantized value, that should be converted into binary form, and the binary form either 0 and 1, it can be in 2 bits. So the 2 bits is either 1 or 0, 0 or 1, 2 bit. Let's take another example here. In this sample, each signal value s of n, the signal value s of n, then we then round a true value to the nearest 4 level. See, the nearest 4 level is the important thing. This process of a signal rounding is in form of quantization. So in the table, whatever the value we are taken, is between 0 to 3 and the binary form is in 2-bit. So whatever the signal is taken, the true value we had taken with respect to compare with another signal, earlier signals, the true value is less. See here, true value is less. True value is less. So for 3.033, we are considering quantized value is 3 and the respective binary number is 1 1. Here in this way, the conversion of the signal is happened. Let's consider with another example is 0.6205, where the contest value is 1 and the binary number is 0 1. So you can consider here the maximum value on the in this particular signal is here, but here the value become low and again the value become lowest is happened. So the signal, whatever the signal is coming, is first low, then peak, then again low and again getting the peak. Let's move to certain another concept of the quantization, where quantization is a process of changing the sample values to discrete levels, rounding whereby a sample value are changed to the nearest levels is the most common form of quantization. So values change to the nearest value is the most common form of quantization. Next point, the approximation of sample using only a 4 quantization level, that is a 2-bit, to store each sample is very crude one. We could great improve the accuracy of our digital information by using more bit per sample, which most engineering application is happening. So most of the engineering application, we are considering a 2-bit value and it is a nearest one, using B bits to store each sample, giving us a 2B quantization level. Now the another new thing is that is a 2B quantization level. 2 bits give, it can be various way. Suppose we consider 2 bits give 4 level, 3 bits giving 8 levels, 4 bits giving 16 levels. It can be happen that 8 bits give 256 level, 10 bits give a 1024 level, or 12 bits give 4096 level, and the last 16 bits give 65,536 level. As the number of level increases, error associated with the quantization operation goes down. Means what? As I am saying earlier, whatever the analog signal you are capturing is, if it is in slowly variation, then the accuracy of sampling is less. But if analog variation is much high, then the sampling rate of sampling is very high. Then depending upon the bits and depending upon the increasing of the bits, the level is also increasing, and which give a high accuracy. Like here for the 16 bit giving the highest level of 65,536. Let's see details of this 2B quantization level. Consider here is certain image of a 3-bit with showing an analog signal quantized using 3-bit. here is 4 bit and again 16 bit, that is in next slide. Notice how accurately sample is happened for the 16 bit. See here, for the 3 bit, here is the sampling rate is there, sampling rate is there. For the 4 bit, see here, only 1 2 3 is in same lane of the 3.5, but in 4 bit it is in between 4 to 3.5. In the same way, here between 3 to 3.5 the signal is there the same way. Okay, now in 16 bit, see the signal is there 1 2 3 4. So more samples per sampling with respect to time is happen with the 16 bits. Now sample can have a fraction value, it can be happen, but it means 0.693 is a fraction value. Fraction value are not a problem, but because of that they can be represented in binary form. It's commonly happen. Usually the quantization interval is not equal to 1 and then signal can be both positive or the negative. It can be happen for it can be positive or negative. So in general, a signal may have a dynamic range. The minimum difference between the largest and the smallest value of an amplitude or the intensities that of the signal is exceeding from plus A to minus A, in which cases a total interval of time of 2A. In earlier phenomenon we consider is 2S. Here the phenomenon with regular time interval is of 2A, which divided into L is equal to 2 raised to B amplitude, and what is B is nothing but a bit binary representation. Let's see in details. The level should be set to cover a full dynamic range of the signal, otherwise there will be an amplitude clipping. Now the amplitude clipping is a new things which is an error caused in the quantization process, where the operation of the quantized level does not cover a full dynamic range and the result in the top and the bottom of the signal base clip off. So the dynamic range have to consider it can be positive to negative, and from top to bottom whatever the signal we are taken is in clip. Okay, so the amplitude clipping is there. Let's consider one example here. See here, it is our normally analog signal and we are taken that sampling with regular interval of time, but here is amplitude clipping is there. See here, it is a severe clamping and the signal quantized using 2 bit. We could have a greatly reduced clipping by making a different choice for the quantization level. It would be better to set a level higher at 0.5, 1.5, 2.5 and 3.5 rather than 0, 1, 2, 3 as shown in here. Same, I am saying that the fractional values, the fractional values can be 0.5, 1.5 or 2.5 rather than the 0, 1, 2, 3. That is for the clipping. Now, it is equally important that the quantization level does not be set too high. The signal being sampled may not be raised above the first couple of levels, in which the case of extra bit is used to represent the higher level will always be 0 or it can be wasted. So most of the times the range represented it is in 0 form, it is almost considered as an wasted. So keep in mind that the binary representation with b bits can be represented as 2 raised to b level. The signal height or the image intensity, the more bits provide higher fidelity. So in higher fidelity, better music, better picture. Let's take an example. So for more bits also require more storage, more processing and the longer transmission. That is a simple our HD picture, HD text or HD video requires a larger space. Let's consider and one interesting fact that CD. If we stored a signal of a music in a CD with 16 bit per sample, then that is the writing speed with sampling rate 44,100 sample per second, then it will be up to this value. It's much higher bits are stored in 3 minutes in the studio. No matter how quantization is performed, the number of bits per sample places the unlimited ultimate limit on the accuracy of digitized value of the information. It is no matter how the quantization is performed, but the combined process of sampling of an analog signal and the quantization of the samples to binary numbers are called as digitization. So digitization is nothing but analog to digital converter, but it is process of sampling analog signal into quantized sample form. The electrical circuit normally electrical circuit that perform the conversion is called as analog to digital converter. Most of the A to D converters are fabricated or an integrated circuits that can be found any places where the analog signal are to be stored, processed or the transmitted digitally. For example, cell phone, computer or automobile that perform as a convergence. So most of the digitalized form gadgets is there like cell phone, computers or in automobiles. It's stored, then processed and then transmitted. In most of the that's analog to digital converter is there. So the quantization operation making an error which cause and representing digitized information. This error are called quantization noise. Because of that effect of quantization error is happened. That sounds like noise in digitized music signal and look like a noise in digital image also. Now the more accurate images or the signal will store the samples or the measurement accurately, the smaller error or the quantization noise will be there. So more accurately, less noise, the less noise can be quantization noise, where we can reduce the error by using more bits to represent each numerical value on computer or in digitalized systems. Now the main thing is that the amount of noise decreases as the number of bit increases and the corresponding number of quantization level increases. So the number of bits is increased, number of noise or the error is less and as a digitalized quantization level can be increases. So the bit level increases, quantize level increases, and highest bit rate, less number of noise will be there. Okay. The amount of noise also depend on the dynamic range of the signal, since the wider dynamic range implies that the quantization interval must be spaced more widely. So the spaced between definite interval of time must be there, and it is also depending upon the amount of noise. To determine the impact of quantization noise in various applications, we must construct a way of measuring the amount of noise. So the amount of noise measured in impact of quantization we require a definite interval of time on which how much noise will be there in between two times interval of the sampling time. So the quantization error is simply the difference between original signal samples and the quantized value. So the original signals samples and the quantized value, whatever the difference is there, that is nothing but our quantization error. Since the size of error in any given measurement of the signal is always relatively with the measurement itself, when constructing our definition of the quantization noise, it happened when we must take into an account the size of the signal we are measuring. Engineers have come up with very important measure of the relative size of any type of noise, even quantization noise also. So this measured is called signal to noise ratio. So for the quantization process, signal to noise ratio, that is SNR, is also an important form, where SNR is a ratio of maximum signal level magnitude to the maximum noise level. So if we consider a maximum signal level is 4 and the maximum noise level of the magnitude is 1, then our SNR, that is the signal to noise ratio, is 4. Means what? A noise level is less noise level, highest SNR. Let's consider with this example. This is the sample sinusoidal with t is equal to 0.01 second. So 0.01 second is total 0.01 second. Quantized bit 4-bit version of sample sinusoidal signals, 4-bit. It's another example of the quantization of the noise between original signals and the quantized version. So here is our sample signals, here is our quantized signals. So in quantized signals, 4-bit frequency we are considering with the sample sinusoid, and the sample sinusoid is actually a 0.1 second time interval. So with the mixing of both the signal, the quantization of a noise, as in we consider as a minimum, the minimum is here, which is the difference between original signal and the quantized version. So whatever noise between actual signal and the quantized signal is here, and that is this is nothing but a quantization process. So here we end to our topic, but before ending we have to understand what we are learned before that, that is digitization process. We know very well digitization process, sampling process, how aliasing is there, what is the aliasing phenomenon, how aliasing is happen, and quantization, what is the concept of quantization, how to avoid it, how to measure it, and how the process is going on. So here we end our topic, that is the digitization, which cover three main things, that is the sampling, aliasing, and quantization. Thank you.